Hello. Today we will talk about printed circuit board assembly techniques. Till now we found out basics of materials that are used for PCB production and also the process of PCB production and used components. Now we have to put these components on the PCB. So printed circuit board assembly is the next production step that we have to know in order to be able to design PCBs as well as possible, that everything in the production goes smoothly. All right, so PCB assembly. And we all know that we have through-hole and SMT components, and in the assembly there are all different combinations possible. So the through-holes can be placed only SMTs, either on top and on bottom or one-sided only, and combinations through-hole plus SMTs on bottom, or maybe SMTs on top and bottom, and so on. So this is all possible, and for each of these combinations there are some restrictions and other things to be considered. So in the printed circuit board assembly, we have in general three main steps. First, we have to apply the solder paste, and then we have to assemble the components, where we can use different techniques as well, and we can also glue these components if necessary. And at the end we have to do the soldering. So let's go into the details how a typical surface mounted assembly looks like first. The surface mounted assembly setup contains these three steps. So first we have to print the solder paste. This is called stencil printer. Then we have to place the components. We can have separated or joint placement machines. There can be several after each other. So one of the machines could be very fast but not that accurate. These are called chip shooters. Or the other could be very accurate but not that fast. These are fine pitch placers. Nowadays these machines are usually combined into a single machine, which is very fast and very accurate at the same time. And at the end there is a reflow oven in which the solder paste is melted. The stencil is made of a thin sheet of steel in the range of 100 to 150 microns, and it has openings where the solder will be printed. The mask in Altium Designer that is used to create this stencil is called top paste for top components and bottom paste for bottom. The openings are a little bit smaller than the final feature to be printed because the paste spreads a little bit on the bottom side when it's printed. The paste is printed through the solder paste printer, which is actually a spatula that prints the paste across the stencil, and several PCBs can be printed at the same time. Well, since everything is done automatically and fast, and there is no second chance of repairing it, the properties of this printing, the parameters of this printing have to be selected carefully according to the paste specifications. You have to be in the green area regarding the print speed and the pressure and angle and other stuff. And the solder paste itself should be very fresh to have a defined specified properties like viscosity. And shelf life of a closed, unpacked paste is maybe 6 months. But when you open it, you have to use all the paste in maybe a week or 14 days. Of course, if you do it manually, you can do it carefully, repair it, and so on. The paste could be several years old, if not even more. But in case of automatic printing, all the parameters should be very well defined. This is how the printing then looks like. So you just apply the paste. This is manual printing, of course, and you pull the spatula over the stencil. This is how we do it at the faculty. This is how our students do it. And then this is how the paste looks like. It is printed over the pads, and there should be no smearing between the pads, at least not too much. Even though the paste may look perfectly, if it is too thick, it would still make shorts between the pins that are close together. So the thickness of the stencil, which determines the thickness of the paste, is also important. To apply the glue, if some of the components are to be glued, is also a machine is used for that. It's called stinger. It applies the glue through a needle. The solder materials used for soldering, well, there are two main groups. One contains lead and the other doesn't. The lead-free solder is also called ROHS, which means restriction of hazardous substances. Actually, this acronym is for the European Union directive, which prohibits the use of lead in electronics. The lead could be still used in some areas, like in medical electronics or avionics or military or space, but and solar cells also. So everywhere where really high reliability soldering is required. All the rest uses lead-free solder. The problem of the lead-free solder, however, is besides that it's less reliable, it's also that it melts at higher temperatures, because the lead solder melts at 183 degrees. So, well, the lead-free solder melts about 190, and this is quite expensive because, usually we use this lead-free solder here, which melts at 220 degrees. And this is quite a problem. And when they introduced the lead-free solder due to the restriction, they had to change the whole other material as well in order for components to withstand higher temperatures. So a lot of changes has been made in 2000, after 2000, where they prohibited lead in electronics. The solder paste is made of very small granules, particles, which have different diameters. So there are several types of the solder paste, and you choose the one according to your components. The most fine pitch components also require the smallest size of these particles. These particles are then mixed with flux. Flux is a liquid that contains alcohol and other ingredients, which makes this paste as it is. I mean, to be able to be printed, and also it sort of prepares the surface, the soldering surface, so that this paste can melt easily and attach to the surface. So it affects the surface tension in order to be this paste to be really well soldered. So soldering flux is a very important ingredient, and it should not, because it contains alcohol, it should not evaporate. This is the main reason of the shelf life problem of the paste. So the components are then assembled using the pick and place machine, and this pick and place machine can be fast or slow. Well, ours is very, very slow because it's old, but for teaching purposes, it's just fine. As you see, it can place maybe a component a second, but in professional machines, if this one places 3,000 components an hour, professional machines can go about 100,000 or even more. The components are placed in a reel. So these are reels. The reels contain maybe 4,000, 5,000, up to 8,000 of components. I'm talking about small resistor capacitors and stuff. but these the larger are then put in trays. These feeders, these reels are then put into component feeders, which then feed in the components which are assembled in a ribbon. Now the trays contain larger components and pick and place machine takes these from the trays then. Components are placed, and this is how the assembled PCB then looks like. Resistors, capacitors, transistors, integrated circuits, and so on and so on. Now this PCB is placed into a reflow. A reflow oven is actually an heating system that contains several compartments that are heating to a different temperature. So when the PCB travels through these, it is traveling through on a conveyor belt, and it is exposed to different temperatures. And this is the typical temperature profile. So we have to heat up the PCB to a certain temperature, and then it is kept there for a few tenths of seconds in order to preheat the whole PCB, and then it's quickly goes into a reflow stage where the temperature goes above the melting temperature of the paste, and then it's cooled down very quickly. So here the inner parts of the sensitive components are not yet reaching this temperature, while the solder paste outside is already melted. And this is important to keep the lifetime of the components as long as possible. The temperature profile therefore should be limited in a certain way. The thing is that here it should not be heated too slowly or too fast. I mean, too slowly is a problem of the how long the PCB is kept at the temperature about the glass transition temperature of the PCB, and being too fast would mean that the components are heated too fast, and that would mean that the moisture would be bursting out of the components too quickly, because each component contains some residual of moisture, and if this moisture boils really quickly and bursts out, it can damage the component. And that's also the reason why components that are sensitive to moisture are packaged in small packages that contain silica gel. And also the most sensitive components have to be kept in a chamber that keeps the humidity below 10% of relative humidity. For example, microprocessors or LED diodes are kept in such a chamber. The soldering phase here, the reflow phase, should be just long enough for the paste to melt, and then it's immediately cooled down. Keeping the PCB too long at this temperature would mean damaging the components as well. So the reflow soldering system altogether is, and together with the pick and place, is shown here at this video. So I will just skip it through a little bit so that it doesn't take too much time. So a reflow oven is a part of a bigger system. Maybe now here it will be visible. So here we have the stencil printer. Let me go back a little bit. So here is the stencil printer. Here is the optical inspection if the paste is printed well. Here you have the pick and place machines, optical inspection again, and then the reflow oven and optical inspection again. Okay, so now we are going through the whole system. The reflow oven, and when you open it, see the PCB are traveling through these heat zones, and this is the temperature profile. Maybe there is another nice image. Okay, this is how the PCB goes through and the melting of the tin. blah, blah, blah. Okay, let's go further. This is the reflow soldering in our oven. We have a small oven that does not have more heating zones, only one. So in this heating zone, the temperature is changed in the same compartment. It has to be preheated, then reflow, and then cooling down, all in the same chamber. It's not energy efficient, but it works, and it's cheap and small. Now you please pay attention how the components are soldered. You will see now that these components are not well placed, and the soldering is not happening at the same time all over the PCB. It will start here, see? And you see also that melting of the solder paste acts with a force on the components, and the components move. And they move in a way that the force is minimized in all directions. And the direction and the force itself is dependent on the way how we design the PCB, how we design the pattern on which the component is placed. So designing this pattern in a certain way would assure that the component will be pulled to the right position even though the placement was not accurate. If you design it poorly, the component may be moved totally differently, and this would make a big issue in the soldering process. Continuing, the amount of solder that is required on the pad is of course limited on top and bottom. The thing is that too much solder would cause solder joints between the adjacent pins and making short circuits. Too little of solder would make the solder joints unreliable. And one of the problems here is also holes. If you put a hole in the pad, a wire in the pad, this would suck the tin through it and it would make the solder disappear. So putting wires on a pin is not allowed, if not absolutely necessary. We will talk also about this when we should put wires on the pin, but in general we don't. See here, there are no wires in the pin, all are outside. And this is how the nice reflow soldered IC looks like. And this is how it looks if you do it manually. As you see, the manual soldering is not as appealing. And one thing more, you see a lot of dirt. These are residuals from flux. Flux, if it's left on the PCBs, then can cause problems like this. What happened here? A voltage between two pins where the flux was applied. Here actually it was applied on purpose just to show the effect. You see that the current starts to flow between these two pins and it causes evaporation. It could also cause heating up of that part, and that's a problem. So the current flowing by itself is a problem. Heating the part and the corrosion that then can happen. So cleaning is important. The PCBs have to be cleaned. If the PCB cannot be cleaned because of some exceptional components that do not withstand the cleaning process, the chemicals for example, then you should use so-called no clean flux. And this no clean flux does not require to be cleaned. What about other soldering techniques? Hot air soldering is one option. You have a certain tool that forces the hot air to the defined area, and by that you can solder the component. So why would you do that? Well, mostly you would do it for repair purposes. And you have manual hot air stations or automatic hot air stations, which then have certain heating components on bottom as well to preheat the PCB to make it easier. So this is more for a repair purposes. You also have hot bar soldering, where you actually have a hot piece of metal that you press against the pins, and this solders the pins. Again, it is intended for a selective soldering. A selecting hot bar soldering, for example, is shown here, when you solder just a connector of some kind or similar to the PCB. So there is a hot bar which is pressed against the connector, and you put the PCB and you solder it very locally. And you need a hot plate. Usually it's here, the hot plate, which preheats the PCB, so the soldering is more fast and reliable. Next option is wave soldering. What is wave soldering? So if you cannot solder in reflow oven, there is a possibility that you solder with a wave. So what's the reason? Why some of the PCBs cannot be soldered in a reflow oven? Well, the reason is very simple. Maybe components cannot withstand high temperatures. And by wave soldering, you can actually also solder components that would otherwise melt at high temperatures. So wave soldering is actually made of a 3 steps as well. So we have a PCB on a conveyor that travels or that takes the PCB through the system. First you put a flux to prepare the surface for soldering. Then you preheat to, let's say, temperature below the melting temperature. And then there is a special wave of solder that pours over the bottom side of the PCB, and the components are then soldered. And the same temperature profile is met more or less as shown here. So you take the PCB, you put it on a conveyor belt. Well, you can put it directly on a conveyor belt like here, or you can use special frames in which you assemble this PCB so that they hold it in place. These conveyor fingers are the most common. But for these conveyor fingers you have to have a certain technological edge of the PCB that is for tooling, that is used to grab the PCB. So that there shouldn't be no components here or tracks. The wave soldering looks like that. So there is a certain system which contains a lot of melted solder, and then there are pumps that are pumping the solder, and here there is a wave that jumps in the air and falls down, and here the PCB goes over it. So that's why it's called wave soldering. This is how the wave looks like. Nice, huh? And now we will go into this video. So the worker is preparing the PCB. Here is the conveyor belt. So he's putting the PCB in the machine. It goes into the machine, and here it will spray the flux. Then it will go into the preheating. And on the other side, now the PCB is preheated, but not too much, so the components can survive that. And at the other end, you see the solder wave waiting for the PCB. So the PCB now enters the solder wave slowly. It is preheated, prepared for soldering, and now it will be soldered. So all the components, the solder just goes over all the area of the PCB, and the components are soldered. Of course, you can imagine that there are certain rules to be used here for the soldering to be able to be completed. Okay, now the PCB is taken away, it's still hot, and all the pins are soldered. Okay, so this is how the good wave soldered PCB looks like. You can see here that only through-hole components are used. So on bottom side there are no components. Well, That's one option, but you can also have SMDs on bottom which are soldered in a wave soldering, like here. So there are some through-hole components on the other side, and there are some SMDs on bottom. And in order for these SMDs to be able to be soldered, they have to be glued, otherwise they will fall off. And it's not a very nice soldering result here. See, quite a lot of short circuits, I would say. At least it looks not very good. This is how the cheapest PCBs are made. Nowadays, if you have through holes, you would always use some form of wave soldering. Okay. You can also have a selective wave soldering. If there are some components on bottom side that are too small, too fine pitch, that are able to be soldered in a wave, you have to cover them. And there is a special material used for that, which is called contoval, and you can make it in order, make it with openings and the shape of the components in a way, for the components in a way that only open parts are then soldered in a wave. So this is for high quantities. Of course, you cannot do, or it's too expensive to do it for small quantity PCBs, and for that you can use mini wave soldering. And this mini wave soldering then has a really small nozzle with solder that is like a mini wave, makes a mini wave when it's pumped through this nozzle, and then this nozzle moves around like here. So this is an example from one of our companies that we are working with, and this is a mini wave that solders selectively just the pins that are intended for wave soldering, and all the rest is intact. So you can have components that are left as they are, soldered with a normal reflow soldering process. So at the end we'll do a little bit of an exercise. So which soldering technology to choose? And let's start with the first one. Single layer PCB. If we only have through-hole components on one side, that's quite easy. Well, we place them and we solder it with wave soldering. That's what we've seen on the previous video. What about if we have a combination of through-hole and SMTs? Through-holes are on top, SMT components are on bottom. Then of course we have to start on the bottom side. We first have to apply glue. Then we place the SMT components, and finally we cure the glue. So the glue has to be cured so that it is hardened. Usually glue curing can be done using UV light or temperature. Then we turn the PCB on the top side and place the through-hole components, and we go through a wave soldering again. In the wave soldering, the SMT components and through-hole are soldered at the same time. So there is no need to place the solder paste here, because solder paste is not needed. It's only wave soldering, and in wave soldering all the tin is applied, all the solder is applied. Now you have to know that here not all SMT components are appropriate for wave soldering. So you have to be careful when you are choosing these components that you choose the ones which are able to be soldered in the wave. Usually if components are too small, too fine pitch, they cannot be soldered in the wave because the pins would just be, so the solder would just make short circuits over the pins. Okay, let's go further. The next option is that we have SMT components on both sides. Okay, and the components that are on bottom are light and small. So we would still again start with the bottom layer, and we would apply the solder paste, and we would pick and place the components. And then we will go into reflow soldering. So the bottom layer is finished. Now we'll go on top. We will do again. We would apply solder paste, we would place the SMTs, and we'll go into reflow soldering. And during that reflow soldering, the light components on bottom side does not fall off, because even though the solder paste melts again, it would still keep with the surface tension, it would keep the components in place. The only problem here is that these SMT components that are pick and placed first go twice through the reflow soldering process. First here and the second here. So any component that have problems with that, with the temperature, high temperatures, are not allowed to be soldered twice. These components should be placed on top, because the top components go only once through the soldering process. So the sensitive components, even though they are small, they should be placed on top. The next option is a double layer PCB that has heavy components on both sides. Here we should add additional step, which is gluing. We always start at the bottom side. We glue the components, we apply the glue, we apply the solder paste, and then we pick and place them. And then during the reflow soldering, the glue cures and the solder paste melts. The curing of the glue usually is in the case in around, I would say, around 160 degrees. So this one melts at 160 degrees, and this one at 220. So before the solder paste melts, the glue hardens, and the melting of the solder paste doesn't move the component anymore. And if it doesn't move it, you have to be even more careful when placing it, that you place it really carefully, really precisely, because when you glue it, it will not move. And before the solder paste melts, the moving of the component will not happen. And when it melts, it's too late, because the glue is already hard. So that's a problem here. But on the other side, if you don't want the component to move and you are able to place it very carefully, then this is a nice feature. Then you turn the system around, you apply the solder paste on top, you pick and place the components, and you do the reflow soldering again. And again, the components that are placed on bottom go through the soldering process twice. So don't put temperature sensitive components on bottom. What about the final combination? Top SMTs, bottom SMTs, and through holes as well. And if there are many of through holes, then you have this option. You start on the bottom layer, you apply the glue, you place the components, and you cure the glue. And then you turn it on top, you apply paste, you place the SMTs, and then you go into reflow soldering. So now the bottom components are glued and placed, the top components are soldered, and then you place the through holes. And the final stage would be wave soldering of all components on bottom. So here the bottom SMT's components and top through holes are soldered in the same process. Again, these bottom components should be of kind that withstands the wave soldering. Now, large numbers of through holes may govern the process in this direction. But what if you can't afford to put only those components on bottom which actually can withstand the reflow, the wave soldering. Let's say that you can afford other way. If you have a small number of through holes, then you can go into a different option. It doesn't matter whether you have heavy or light components on bottom here. You can glue them or not. Here, this is an example when you have light components on bottom and small number of through-hole devices. Then you go first applying solder based on bottom side, you place the SMTs, you go to reflow soldering, then you change you switch on the top side, you again apply the solder paste, place the SMTs, and go reflow soldering again. Then these light components do not fall off. Then you place the through holes and you go into selective wave soldering. A selective wave soldering can pay off if the number of components which are to be soldered is very low. But as I said, what if you have the same combination but you have complex SMTs on bottom and top? Then they cannot go into the wave soldering. So you go into reflow soldering on top and bottom. And then you place the through holes and you wave solder by selective wave soldering. So selective wave soldering can be used if through holes are not too many, or if the bottom components are not allowed to be soldered in a standard wave soldering. But usually through-hole components are made of plastics and materials that cannot withstand high temperatures. Therefore, wave soldering is the only options. For example, connectors. Connectors would melt at 250 degrees, let's say, in wave soldering, in a reflow soldering system. But if you have a through-hole component that can withstand high temperature, you can get rid of the wave soldering. You can use so-called pin-in-hole reflow system. So for high temperature resistive through-hole devices, you can go differently. You start on the bottom layer again, as we are used to, go to reflow, and then turning around, applying paste on the SMT pads and also through-hole pads. And then you go into reflow soldering once again, and this is called pin-in-hole reflow, where you reflow solder through holes and SMTs at the same time. As I said, the through holes should withstand high temperature. They also have to have small spacers below so that they do not sit on the surface directly, so that the solder paste can be intact, and the amount of solder paste should be large enough to be enough for the whole wire from top to bottom. I never tried it myself, I must admit. A pin-in-hole reflow can be used also for a single-sided PCBs where all components are on top. Again, very simple. Applying and soldering in reflow. So choosing your appropriate process for the soldering affects really your design. So you, of course, can choose whether you would use SMTs and through holes. And in my opinion, nowadays, you should avoid through holes as much as possible where needed, or where absolutely necessary, you use through holes, and then you use the selective soldering. So using SMT assembly is preferable. It's preferable to use it on a single side if possible. And as I said, for through holes, you should maybe use it only for connectors or other unavoidable components. And for through holes, selective soldering, yeah, selectively wave soldering, or even wave soldering of the whole PCB is okay for large quantities. And if the components, SMT components, are on both sides, then on the bottom side use light components that do not require gluing. So at the end, it's all a matter of price. So you should really pay attention at the design phase to make your life easier when the PCB goes into production. So finally, after this lecture, you should be able to describe all the production steps, different soldering techniques, their strengths and weaknesses, and you should be able to choose the most appropriate assembly technology according to the type of the printed circuit board and the type of components. And here is some literature where you can check it out, some books and some website of the components that offer PCB assembly. And that's all for this lecture.